All right, so last week we talked about site control and we went through the process. So again, I'm going to just buzz through this real quick before we get into this stuff that we're talking about over the next couple of weeks. Use of control, which we're going to actually really see how that kicks in uh, once we get past this first test. So it's going to be primarily a very, very important aspect of everything you do. What we've been talking about was establishing control. So that's what this traverse process is that we're going through all that math for, okay? So the calculations, we established, we started that last week. We're going to finish that this week. And I'll give you some more homework problems to work on that. And then we're going to go out and do that class exercise next Thursday, okay? So we talked about the different types of control, um, horizontal and vertical control. So primarily what we are looking at is horizontal control right now. Vertical control, elevations, those kind of things, we'll be talking about that in the 6th week a little bit more. So we are focusing in on just bringing in primary horizontal control, giving ourselves either an XY location or a northern and easting location. So primary control is essentially what we were establishing. That's your permanent kind of stuff that has to last throughout the whole project kind of idea. And so that's kind of what I'm having us walk through. And actually, when we get out and start dealing with our labs out in the front yard of the school, I actually have a control network out there that we would consider primary control. It's a pretty high order. It's been there for years at this point, and so we're going to kind of see how that works and how we use that. Secondary would be of a lower order, as we talked about last week, and it's usually used to supplement your primary control. So what we're after really in this class is providing what we call working control, very temporary. It's just used to construct whatever feature you're laying out. So we haven't done any of that yet. And we will be doing that, like I said, when we start getting into week 6, 7, 8, those are going to be where we start working with that working control kind of concept. All right. So establishing the control, we are dealing with what we call a traverse. And remember, just a traverse is just a polygon of some type, typically consecutive lines where you measure the lengths and you measure the angles. So that's what our field exercise is going to be doing on our Thursday. We're going to go out, set up our traverse. Actually, I'll probably already have the traverse set up for you. You will just occupy the stations, do your measurements, and then you're going to come back in and do the coordinate or the calculations to see kind of how they did. I did mention that you probably won't do very well in terms of your precisions. And again, that's okay, because what we're really just trying to get you to think about is, the process and getting the quality experience as opposed to actually getting the good numbers. But of course, in the real world, you have to have good numbers. So this is just a leading into that. The two types of traverses we talked about were open and closed, and we said that we would never use an open type traverse. So what we're doing is what we call a closed traverse. Closed traverses fall into two categories, either the link or the polygon type. We are doing the polygon type, and that's the only kind of thing we're going to deal with. All of the math that I'm showing you and all of the precision concepts and all of that works exactly the same way. So it's not any different to do that type of traverse. It's just we're not going to perform that. And the reason we use closed traverses is because we get a check directly on our measurements. And the two things we're measuring are angles or distances. So those are good things. So this type of traverse is used extensively for control. And it's for just the average working surveyor or even layout person out there, it's a really good way of establishing control. Now, people that are using GPS are doing things a little bit differently. They're basically just getting a coordinate. They're getting high-level control, but they're basically, your control is your satellite constellation. So essentially, you can just set up anywhere, tie into your satellites, and you're getting a calculation. But there are a lot of things that have to go into that also. So we're not going to talk about that in this section. We might do a little bit of GPS towards the end, but in general, we're looking at more ground-based stuff. All right, so app open traverse obviously shouldn't be used. We're not going to talk about it. So this is the things. I'm just going to buzz through these real quick, and if anybody has any questions while we go through this, just please stop me. But hopefully you're going to get to know these things, and you can break it down into about 7 different things of areas that we're going to deal with. So the first thing is, after you've measured your angles and your distances, you go through the calculations. The first thing we talked about was balancing angles. Then we calculate a direction. We either use that azimuth or bearing concept. And as I mentioned in class the other day, on Thursday's lab, that the azimuth has a distinct advantage because it generates a sign for you, so a positive or negative sign. So that's great when you deal with that. Once you've got good bearing or azimuth direction, then you can calculate your latitude and your departure, then your misclosure and your relative precision. Then we adjust the traverse, then we do the coordinate calculation. So it's an actually very easy step process to deal with. So remember, the first thing we do is balance angles, and since we're dealing with the closed type, we would be looking for a misclosure where we sum the interior angles and we check that against the theoretical sum. And then we look at that theoretical or that misclosure value, and if that is below an acceptable value, then we reject it, which would indicate that you have to go out and remeasure stuff. If you're balanced, or if your angles are determined to be within an acceptable tolerance, then you're going to what they call balance angles. Really, I like the term adjusting angles better, but what we're doing is some kind of distribution. And we're going to use that correction there where we just take the misclosure and we divide it by the number of angles and distribute it equally. And we talked about all the other reasons you would weight things and those kind of things. So again, just a quick go through. So once you've calculated your adjusted angles, then you're going to calculate directions. And I hope that everybody's pretty much tapped into that at this point. You shouldn't be struggling with bearings or angles or azimuths at this point. If you are, then make sure you contact me so we can go through some of that. I can work with you independently if that needs to happen. So when you do the azimuth, you always have to have an initial starting direction. So that could either be an actual direction or an assumed direction, and very often it's just assumed. And the reason is because we can always rotate this figure into some kind of shape once we get done if we need to. So that's not a big deal typically. You always use your balanced angles, because if you don't use your balanced angles, then your azimuths, if there's a bust in the angles, there's going to be a bust in the azimuths, so, or bearings. So we do that. Then we calculate latitudes and departures. Okay, so remember, you can think of each line of your traverse, each line is a vector, and that vector is composed of two components, the latitude and or the departure. So the latitude is equal to your distance of your course times your cosine of theta, where theta is either a bearing angle or it's an azimuth angle. And the departure is your distance times your sine of your theta. So make sure you understand that. And those equations, I would just memorize those two because we're going to be using them a lot. You're going to see these two things used extensively today, or getting started into it today as we get into it. And again, if you're using bearings, then you have to assign a positive or negative to your latitude and departure based on the quadrant that you're in. If you use an azimuth angle, the beauty is that your calculator will bring the sign with it. Okay, so again, just remember that and think about that. So for bearings of a northeast, remember north and south are your latitude directions, and east and west are your departure directions. So for a northeast, you are positive departure, positive latitude, and for southeast, you're negative latitude because you're traveling in a negative north direction, if you will. And then you have an east is positive. And then for the other quadrants, southwest is negative, negative, and That would be in terms of latitude departure. And then northwest would be positive, negative. But again, if you're using a calculator in terms of azimuth, then it will do all that work for you, okay? So we said that once we have latitudes and departures broken down, we can then determine and talk about what we call linear misclosure and relative precision. These are the big areas because this is going to determine for you what you're going to do with this traverse, whether you're going to accept it and adjust it or reject it and completely rerun it. So if we sum the latitude column up in that diagram that we were looking at, the other day, you get what's called an error in latitudes. So theoretically, we know that the latitude should be 0, but that doesn't work. So we usually have some kind of error. And then departure would also have a summation of your departure column, and you'll have a departure kind of concept going on. And then we can determine or talk about what we call a linear misclosure, or also referred to as an error enclosure, usually defined as E. And so that's just the Pythagorean theorem use of your error in latitude squared plus your departure squared. You take the square root of that. And the bearing angle of that is less important. So the E is the thing that you're going to use to calculate your precision. So again, we've gone through all this. That's why I just want to briefly go through this, and we'll see this again on Thursday. So okay, so for your precision is expressed as 1 unit of air and so many units of distance traveled. So essentially, you take your linear misclosure, your E, and divide it by perimeter. And if you do that, you get a really small number. You just basically take the reciprocal of that. What we get that then is, this is really saying that you have a half a foot of air and 8,520 feet. But we like to express that in terms of 1 unit of air. So this says that we have 1 in 16,385. And a lot of people would just round that to 6,400. So it doesn't really matter that you talk about smaller numbers here. The 16 is the big thing. So 1 in 16,000 essentially is saying that for every 16,000 units we travel, we can expect 1 unit of bust, plus or minus. So if this is in feet, then you're talking about 1 foot. If that's in meters, then you're talking about 1 meter. And as we talked about before, this would be really not a very acceptable traverse. This would be one that you would pretty much reject. You'd be looking you'd really realistically probably only be about 1 in 50,000 as your base minimum. And you should ideally be getting much better results based on the type of instrumentation that you're using nowadays. But if you were using a transit and a steel tape back in the day, this would have been an ideal number, because they basically expected about a 1 in 10,000 closure back in those guys. So we're talking like in the 30s, 40s. 1 in 10,000 probably would have been very acceptable. So this would have been actually pretty decent. Okay, so we talked about adjustment rules. We're only going to consider the compass rule, which basically assumes that your angular accuracy and your distance or linear accuracy is about the same. So what it's going to do is when it adjusts the traverse, it puts the air equally in both the angle and the distance. So what it's really doing, and we're going to see this on Thursday, but what it's really doing is tweaking the latitude and the departure in such a way that you're going to get a little bit of change in your angle at each vertex, and you're going to get a little change in each distance. So the transit rule, what I said in class the other day was that assumed that you measured your angles better than you did your distances, which was probably true back in the day when they were utilizing it. So when you did the transit rule adjustment, it would work it in such a way that it would essentially hold your angles fixed, but it would put most of the error or the adjustment into the distance. And you can probably not even find a transit rule calculation anymore in any of the textbooks. You used to be able to see that in a textbook. They don't even talk about it in your textbook because it's such an older method. So the newer methods are Crandall's or least squares. they're way beyond the ability to do this stuff by hand. So this is stuff that we would do more statistical, and it's very rigorous. A lot of people use it because it's gives you a really good adjustment, but it's done strictly by computer. Okay, so for the compass rule adjustment, we have to do two things. Remember, we have to calculate corrections and then we have to apply them. So basically, the calculation for any latitude is going to be your error in latitudes divided by your perimeter. And that's going to be then multiplied by the distance of the line you want to correct. So if you have 5 lines in a traverse, you're going to have 5 corrections of latitude and 5 corrections of departure. Then those get applied to your latitude and your departure. So this is your a raw latitude and departure, and your adjusted is going to be equal to the lat plus the correction. So you're going to do that across the board, which we did in class. And if you've done it correctly, when you sum up the adjusted latitudes and departures, it should go to 0. So that's the whole idea of this whole process. So the last step is to talk about coordinates, which we're going to be jumping over here in a minute to talk about. So coordinate calculations are based on your latitudes and your departures, and then they are based on what I call a seed coordinate or a starting coordinate value. And again, that can be arbitrary, or it could be something that's a fixed number that's tied into the real world somewhere. So basically, any northing B would be equal to any northing A plus the latitude from A to B. And we kind of saw how to work that out. So you're going to use your adjusted latitudes and adjusted departures. So that's what these represent here. These are your adjusted latitudes, and departures. That'll get you your coordinates. So the coordinates are all important. That's what we're after at the end of the day, as we talked about. Okay. So if you're using X's and Y's, you have to flip latitude and departure, because X is going to be in a departure direction and Y is a latitude direction. And the reality is my experience is most people do not work in X's and Y's in the land type of business or layout. Most everybody works in a northing and an easting. But you do have to be aware that some people might. And so if you're giving people data, you need to make sure that they understand what data you gave them. And also if you've gotten data from somebody that you're knowing whether you're northing and easting or X's and Y's. So you will be seeing it kind of in both formats. So I think mostly in your book and most of the stuff that I'll be dealing with is northing and easting, but we'll talk about that a little bit more here because we're going to start to get into coordinate calculations. So, okay, so that was last week's. Does anybody have any questions on anything that generated before we go into the new stuff? Anybody think of anything?
I'm good.
Okay, well, I will be answering questions then on Thursday. So make sure that if you do have a question that you will bring that up to me on Thursday, okay? So we're going to go into coordinate geometry now. So I'm going to be dealing with this over the next 2 weeks in lecture because there's a lot to this, and you know it's not hard, but we're going to be doing a lot of the math stuff. So I'm going to kind of present it today. And probably next week we'll be working just a little bit more homework problem type stuff via the Zoom session. So let's go ahead and get started. Does somebody have a question?
Yes.
Yes.
The traverse that you gave us to work on that you wanted us ready for Thursday.
Yes.
Is that ready to turn in, or are we going to be going over it?
No, just none of this stuff is going to be turned in, okay? Until we get to labs, then you're going to be doing lab reports that you submit to me. Okay. So all of this is just homework for you to do and to make sure that you're understanding the concepts, okay?
Okay, thank you.
Yeah, so yeah, don't worry about turning it in, but just because I say that doesn't mean, well, okay, he's not taking it, so, you know, I don't need to do it. That's not going to work that way, as you'll find in the first test. So all of this homework, it's expected that you're doing it, okay? Because I'll find out real quick that whether you're not. And, you know, the quizzes are kind of focused to help you guys think about what you're, you know, mastering or not mastering. That's why I try to do a quiz once a week as well. So, okay, that's a good question. All right, anybody else? All right, so let's go into this week then. And like I said, we're gonna I'm gonna be doing this over 2 weeks essentially. So this will be weeks lecture 3 and 4 essentially. All right, so we're gonna introduce this concept of coordinate geometry, and this is like one of the most powerful things that has been developed in any recent time, and particularly in software that you use. A lot of software that you use is really coordinate geometry type based software. And in fact, you can kind of think that AutoCAD is using coordinate geometry, even though they don't typically say it. But the original coordinate geometry programs that were written for civil engineering and surveying go back to the 70s, and they're typically called COGO. And what they're doing is that's an acronym taking the C and the O from the coordinate and the G and the O from geometry. So the professor, I think the professor that developed coordinate geometry type programs, I think he was from Florida, but he coined that term COGO. So if you hear that ever, that's usually talking about a coordinate geometry type program. And again, indeed, I would say that AutoCAD is a coordinate geometry type program. So we're going to look at some coordinate systems today. I want to talk about the 2D, 3D systems, and also being able to convert back and forth between them. Now, I'm not going to do much with conversions on you, but I'm going to show you that there are some things that you can do to go back and forth with these. And then there's what I refer to as a hybrid type system. And a hybrid type system is a case where you're typically dealing with highways. So I'll introduce that today, but we won't see that until we get to the highway stuff back in like chapter or week 8 or 9 or something like that. So those are going to come back to get us at some point. So primarily what we're going to focus in on over these next 2 weeks is coordinate calculations, and know how to use this stuff and kind of fluently do this. And that is, if you learn some of this stuff, it's really extremely powerful for not just this class, but for other things that you do. So we'll kind of see how that works. And then I'm going to touch on this concept of state plane coordinates. It's not as important for most people, but a lot of people don't understand that this kind of thing is out there, and they'll get sets of plans that are based in state plane coordinates, and then they're using them just like normal coordinates. And that's a big mistake, because that's an incorrect way of doing it. So I'll show you kind of how that works, but we're not going to get into it that in depth. Now, any of the surveyors in the class, they need to understand state plane coordinates a whole lot more. So eventually you're going to get a class in control surveying where you talk about state plane a lot more in depth. So that's kind of what we'll be looking at. All right, so let's talk a little bit about coordinate geometry. And the one thing you can truly say about this, that it is an extremely powerful type of tool, and it is useful for so many things. And just like I said, anybody doing layout, whether they know it or not, they're using coordinate geometry. Now, some guys use it a little bit more than others, but a lot of guys that are just using, say, data collectors, and they're basically pushing buttons and everything, what's happening on that data collector, it's all utilizing coordinates and doing this coordinate calculation. When I first started back in the day, there wasn't all this fancy automated stuff. So we were constantly pulling out our calculators using those coordinates, and we were calculating pretty much everything or anything that we needed. But nowadays, people don't have to do that. And of course, the downside to that is it dumbs you down to the point where some people you can teach them how to use the software, but they don't really know what they're doing. And then of course, if you encounter a problem, you don't know how to fix it. So there's kind of a lot of issues. But if we look at some of the advantages of coordinate geometry over doing things the older way, older style, this basically allows you to do very, very quick layout. So it's very compacted information, and having all your things in coordinates, basically it's very quick. It also will typically yield less mistakes. So you can occupy one point and turn angles and go distances from that one point without actually having to set up a bunch of different times and turning all these things to get to the point that you need. So it really facilitates that. The information that you get in coordinates is very compacted, and it's usually in a tabular form. And basically it's just what you see as a point number And then you see what's called the northing and the easting value. And you may have, you may have 500 points on your job, and it's just like a spreadsheet where you have, point 1, point 2, point 3 with its northing, easting, and possibly also elevation. If you have vertical control information on there, that might be on there as well. But by having that tabular form, I can calculate anything I want. So if I need a distance between point 1 and point 50, I can calculate it. I don't have to have a diagram that has all this stuff on there. So that's why they put it in that tab form. And if it's downloaded into a working controller, like a data collector or something, then all that information is there. You don't even have to type it in. Also, we'll find that complex types of calculations can be done very, very rapidly. So instead of using a bunch of triangles to calculate things or other methods when you do all this math, you can do it very simply streamlined when you get into complex calculations. So again, probably has more to do with doing things by hand than anything, but it's just true in the way that it's working. And so coordinates are very, very adapted to digital devices. So that's why we see this stuff so much. So obviously computers, they're calculating in any software that's running this kind of stuff. So typical software that we see for layout purposes would be things like you can use AutoCAD. If you've ever heard of Trimble, Trimble is a big manufacturer of GPS equipment and other types of surveying equipment. And they have a program called Trimble Business Center. It's called TBC. It's used quite widely. And it does COGO calculations. And then there's Carlson software. So there's a lot of different types of softwares out there that would run on computers. So data collector, we're going to talk about data collectors later on in the semester. It's basically a little smaller version of a handheld computer. They're fairly sizable, some of them, but you can actually get them not much bigger than a cell phone nowadays. But they interact with your instrument, and your instrument will feed information to the data collector and vice versa. But your data collector is also able to do, well, you can actually download AutoCAD files onto it, so you can actually visualize everything. And you can also calculate stuff. And the beauty of data collectors, one big thing is that there's no handwritten notes anymore when you use a data collector. All of the information, when you turn an angle or you shoot a distance or any of that stuff, that all goes straight from the instrument into the data collector. No transpositions anymore, or somebody missing a character or any of that. That doesn't happen. And then total station instruments themselves, you can actually work with coordinates directly on a total station because they have onboard processors too. So you don't even need a data collector if you're using a total station. But a data collector will give you much more power and more calculation capabilities. So again, coordinate geometry, there are so many advantages. Everybody uses them out in the world, in the real world now. Nobody's doing anything other than coordinate geometry. Okay, so when you're talking about the use of coordinate geometry, it really coordinates construction projects, and it benefits every type of coordinate, every type of project you can think of, from the smallest type of thing that you would ever do up to massive types of structures. So for things like buildings, whether you're talking, just a simple house layout that's maybe just a simple rectangle, up to a big building like, say, the stadium they're building down for the soccer team that's happening. I mean, all of that kind of stuff I guarantee it's all facilitated through coordinate processes. And then you get to really, really big projects like, say, bridges and dams. Coordinates definitely facilitate this kind of stuff. Mining and tunneling, I mean, a lot of you may have no experience or are thinking about that, but all the mining that goes, or tunneling that we have happening, it all happens with this. You guys might recall there is a tunnel that runs from London over to France underneath the sea that separates them there, the English Channel, and they built that with big tunnel boring machines. And they started in England and bored, towards the east, and then from France they came over to the west. And these guys were using coordinates basically, and when they hit, they were off maybe just like maybe centimeters in terms of where they were supposed to be. So it was pretty amazing, and all of that could have been facilitated, or was facilitated, using this coordinate geometry concept. Highways, everything on a highway now is done through coordinates of some type. A lot of them now use very high level what they call machine control when they're dealing with highways. And all of your coordinate files are downloaded to a controller that's in the cab of either your dozer or your grader or whatever. And that has also servo motors that are attached to the blades. And so your operator just kind of watches the screen, and the thing pretty much drives itself based on your coordinates and raises and lowers your blade as it needs to. So all of this, again, facilitated by coordinate geometry. Utilities of any kind, you know, from a small sewer to a large pipeline, those kind of things. So in a nutshell, you can say all types of site work are going to be based on coordinate geometry. Okay, so let's talk about coordinates a little bit. We can kind of classify these guys as different types of coordinates. So you have ground coordinates, or what I would refer to as terrestrial coordinates, geodetic coordinates, which is typically talking about the concept of latitude and longitude. So those are usually very, very high precision types of things. And then you have what are called planar coordinates or plane coordinates. And one high level subset of that is a state plane. So what many times people are working with is what we would call a ground coordinate. So when we're out there working with a total station and measuring stuff, we're just on the ground. We're generating terrestrial coordinates, but we're going to project everything to a plane. So we're going to have a localized plane there that doesn't really, we don't see it, or it doesn't really exist, but you know, that's what you're dealing with. So a geodetic coordinate, when you're talking about latitude and longitude, that's actually on a sphere. So that's not a planar type of coordinate. So those are really high level stuff, and anybody doing layout is not using that kind of coordinate at all. Now, interestingly, GPS does use that, but it's all converted to whatever the user wants via the controller. So again, there's a lot of calculation going on behind the scenes that the user doesn't even see. It just spits out a northing and an easting form. So plane coordinates then refer to the fact that you are projected to a plane. And you know, normally we do that. So we're going to be working on some kind of plane, whether it's an arbitrary plane. It could be, if you're working in a building, you may just have the plane like on the first floor. That's your plane. And if you're dealing with state plane, that's a way of handling geodetic coordinates and getting it down to a plane. But the problem is that plane is not at ground level. So that usually has to be projected up or down. So again, we'll talk about that a little bit more. In general, though, we're going to be talking about what we call plane coordinates. That allows us to use Euclidean type geometry, planar geometry. We don't have to worry about the spherical aspect of anything, especially again, because our projects are very small. Now, people that do deal with very large projects like highways. So if you're dealing with a highway calculations, let's say that starts in Cincinnati and goes to Dayton, you have to deal with curvature when you talk about that. So you can't just talk about one unique plane. So that does have to get into other aspects. And we're not going to be dealing with that. We're going to keep everything really localized, very simple plane. Okay, so when we talk about coordinate systems, let's talk about the different types that we have. The first kind we would talk about is a two-dimensional type of system. Typically, there's two that we're going to look at that we recognize, and most of you are pretty familiar with. The Cartesian or rectangular, and then we have what we call the polar system. So those guys usually follow very definite conventions that we'll talk about here. Then we have the three-dimensional Cartesian, cylindrical, or spherical. So all we're actually doing is now adding a z to this, a z value. So basically, with the Cartesian two-dimensional, if you convert it to a three-dimensional, you're just adding a z value to it. With a cylindrical, it's basically a polar coordinate, and what you're doing is adding a z value to it. So a spherical is the one that's more unique, and that's a latitude and longitude type of system. So we're not going to talk about that too much. And then the hybrid system is basically kind of like a Cartesian, but it's also different the way it works. So I'll explain that. So let's take a look at something here. I want to move over to my screen real quick and make sure that we're understanding some of these issues. I need to open this. I didn't do that. Okay, so when we're talking about the two-dimensional Cartesian, I think everybody understands this, but you have the two unique axes that you would be talking about. So you have one axis here and one axis here, and we think about the fact, okay, those are your directions. So if you're talking about the typical X and the Y system, we could also think about that, or superimpose on top of that your northing and easting. So we're going to use those interchangeably. So most of the time we use what's called the right-hand rule. And we have this guy, this is your origin. So that's your origin. And with that, that's our reference for 0. And we like to keep everything up in that quadrant. Everybody knows that, because we want to keep everything positive. They do have terms they use mathematically. You guys might know this is referred to as your abscissa, and this is referred to as your ordinate. When you have the right-hand rule, what you're saying is angles turning this way are going to be positive. So again, you're used to AutoCAD. AutoCAD uses right-hand rule. A lot of things we deal with in math. Now, some of the things we talk about in surveying, that's not true, because when we turn an angle this way in surveying, we usually consider that as a negative angle. This way is a positive. So there are subsets of that you got to think about. Okay. So the one thing about this Cartesian coordinate system, again, I think everybody knows, is if I have a point, let's say defined right there, I can reference that down to this axis. So in other words, you measure that distance. Let's say I measure that distance, and that distance is 5. And then I reference this over to here, and this distance is 7. So this point is defined as 5, 7 in the x, y world. But if that was a northing and easting, it would be 7, 5. So I believe everybody's cool with that. So if we look at the other system, which is a little bit more, a lot of people don't understand as much as the polar system. The polar system basically says, okay, if I take a vector from, let's say, here to here, and I measure that vector's distance, sometimes referred to as the radius, and I measure this angle, which a lot of times is defined as theta, I can give that guy values and reference that. So for instance, let's say you measured this radius as 60 or 80.6, and let's say this was 54 degrees, 12 minutes, and 32 seconds. The coordinate of that point then would be expressed as that. And if you're doing it in AutoCAD, you guys probably know you don't use that, you use the less than symbol. But those are two different systems, and it's possible to convert one system into the other. So I can take this system and convert it into a rectangular, or I can go vice versa. So just talk about some of these real quick. If you want to go, let me see if I got these. I think I might have these on my PowerPoints. We'll come back to this slide in a minute. Let's see. So if we want to convert Cartesian to polar, there's basically two equations that you're going to use. So if you have a Cartesian x value and a Cartesian y value, you can calculate the radius by taking the x value squared plus your y value squared square root. And then you could also then take an inverse tangent relationship of your y over your x. So what this is saying, again, if we looked, and we're not going to be, well, we are actually going to be doing a little bit of this. This actually is a little bit more important to us as we get into this. So if we look at this here, let's go back to So what we're saying is this. So if I have my point, my initial point, and that initial point is here, and we said that point was sitting at 5, 7. So again, that's this value versus this value. This is telling me I can calculate that radius. I can calculate the radius, and I can calculate theta based on that conversion. So what we said was the radius is going to be equal to 5 squared plus 7 squared square root. And what that would give us, as you see if you do the math, is the number I just had up there. So it would give me a linear distance of that. And this would be an arc tangent of your y value, which is going to be 7. So we take 7/5 arc tangent, and what we get that 54, 27, 44. Okay, so this is again taking us from a rectangular coordinate into a polar coordinate. Okay, so we will do a bit of that actually. So that's one thing, and I'll do some more homework problems with you as we get into this. So let's see if we go back the other way, how you can do that. And essentially, we've already talked about that because that's kind of what we did when we got into the stuff last week. So a polar to Cartesian conversion conversion is really just taking it and breaking it down into what we would call Latin departure. So you basically can take and calculate any x value by taking your radius times the cosine of theta, and y is going to be r times the sine of theta. Now, in this equation, you need to recognize a couple things here. The way I'm expressing this, I just want to show you, because I'm doing it mathematically, and that's not necessarily the way you're going to see that in terms of layout stuff. Okay, so let me just break this down real quick. Just going to do a new one real quick here. So I'm going to draw another picture that relates this so you can kind of see what I'm talking about. So if this is my two axes and this is my angle, let's see, we're going to say we have an angle like this. So here's a couple things you got to recognize about this. So this is we're going to call this the x, we're going to call this the y. In this case, notice that my theta angle for that expression is measured off of the x. Well, we're going to say that that is 64 degrees, just to reference that. And we're going to say that this is 12 units long. So that point right there is sitting at 12, 64 in terms of a polar coordinate. So to convert that to an x and a y, you can see that you're going to take your x is going to be your distance times the cosine of 64, and your y is going to be 12 times the sine of 64, and what you'll get is 526 and 1079. Excuse me. So does anybody notice that this is exactly what we were doing with latitudes and departures? Does everybody see that? Anybody not see that?
Yeah, that's right.
There's something that's really different though. Does anybody know what's different about these equations? Look at your angle. Where's your angle being measured from?
From X, not
Yeah. Yeah, it's from the x instead of the y.
Yeah, so this equation, notice this is x cosine relationship, but for this is actually for us, this would be departure. You see that? Does everybody see that? But if you notice when I defined latitude for you, we used the cosine for the latitude because we actually use this angle here. Okay, so you got to be careful because I'm doing the right thing, but I've got to make sure whether that angle is measured off of the horizontal or off the vertical. Okay, So remember, in this case, X is actually departure, and this one is actually latitude. But if you go back and look at my latitude definition, I said latitude is distance times the cosine. And that's true, but the angle is measured here, not here. Okay, does everybody get what I'm saying there?
Would you advise to do it like this and just remember to flip the two, or could we just use that other angle and then do it like we do normally with latitude and departure?
Yeah, here's what I advise. Okay, first off, when you're dealing with like control, like we're dealing with, and layout, use the term latitude and departure. Okay, and then it's pretty much of a lock, because latitude and departure is always talking about, this is latitude, this is departure, right? And the other thing is we're always talking about the angle off of the north. So we're always using this angle, not this guy. Okay. So I just want you to be careful, because there's a difference in this equation than it's just flipping it. Okay. You're not going to be doing this kind of stuff too much right here. All right. This is more of a thing you would do in math. Okay. But that's how they present it. So I just wanted to show you the difference. Are you okay with that?
Okay, yeah, I get it.
Yeah. So really, realistically, here's the equation that we're going to be utilizing all the time. Latitude is equal to distance times the cosine of your theta angle, which is bearing or azimuth. Okay. So the key thing is this guy. That's either a bearing or an azimuth. It'll never be a horizontal. It'll never be an angle measured off of X. Okay. We never do that. And departure is the distance times the sine of your bearing. So these angles, where they're calling it theta generically up here and I'm calling it theta, that's not the same angle. Okay, just be aware of that. Okay, that's a good point there. Really, really good point. So again, math and physics, they like to do it this way. Land, surveying, engineering, we like to do it this way. Okay, so it shouldn't be a big issue, but just you got to keep in mind. All right, but here's what we're going to use constantly, this and this. That's what we're going to use all the time. Okay, does that make sense?
Yep.
All right, so let's see. Wait a minute, I get back to my spot here. Got too many things open, I think, here. Okay, here we go. All right, so this is talking about three-dimensional. I'm not going to get that deep into this, but there are conversions that you can do from one to the other. But I just want to show you. This is showing you, I think everybody can see, in a 3D realm. And so you can see our 3D grid down there, the kind of little data dashed lines. And you can see our XYZ in terms of right-hand rule. And our point is sitting above that grid at 5, 5, 5.5. So you can see how that's referenced. 5 in the X direction, 5 in the Y direction, and then you're 5.5 units above the grid. So a lot of site work isn't an XYZ format, although we would normally call that northing easting elevation. So instead of XYZ, we would call it northing easting elevation. But again, for this picture, it's just the same. It's just a different way of stating it. The next couple of slides here we're going to see, I want you to understand that they're all the same point, but we're defining it differently. So this is a Cartesian XYZ. So it's taking that two-dimensional and now adding a Z to it. So if we look at that in a polar format, we have this guy, which is called a cylindrical coordinate. Notice your polar coordinate is down in the grid. You have a radius value and you have a theta angle. And notice what we've got is the radius is 7.07 and the angle is 45. Now, that came from that 5, 5, okay, for X and Y. And the Z, notice the Z in this is the same as it was in the other system. Okay, so this is the way this would be expressed as a cylindrical coordinate. This guy, that's your radius, your angle in the XY plane, and your Z value above the XY plane. Okay, so again, that picture and that picture are exactly the same. The only difference is the expression of the coordinate system. All right, now you don't see too many cylindrical types of coordinates given out in the field. Okay, so either because of the way your instrument works or your whatever you're doing, that's not what you're really doing. You're really kind of using this kind of coordinate most of the time when you're out there. Now, here's the kind of interesting thing. This, which is called a spherical coordinate, is what your instrument is actually doing. So if you're using a total station, it's measuring the angle in the XY plane, the one that's down in the grid. It's measuring the angle from the grid up, or it could be from the zenith down, either way. And then it's going to measure that slope distance, which I'm showing a radius. So that radius there is the radius of a sphere. And so you can see what you get is a radius and an angle in the horizontal plane and an angle from the XY plane. And again, that point is the exact same point, 5, 5, 5.5. And this is really what a surveying instrument gives you, a total station. Just think about it. You turn a horizontal angle, you turn a vertical angle, and you shoot a distance. What you're actually getting is a spherical coordinate. But when you're out there in the field, you're not working with those. You're working, oops, I'm going the wrong way. The wrong way. You're actually working with that kind of system, okay? So normally you'd have to do conversions. The good news is that when you're out there turning that angle and the vertical and the slope, what the instrument's spitting out to you is this right here. So you don't have to do any of that high level conversion. But just to show you, you can do it. You can convert a Cartesian to a spherical. Okay, there's your calculation. I'm not going to go through it. You don't really need to know how to do this, but it's interesting to see. And then those are some ways you can do it. So let's talk about another type of system, which is what I consider a hybrid system. It's in the highway world, it's called a station offset typically. So what you're dealing with is your station and your offset. Those are basically a Cartesian, okay? And then you have an elevation, which is just above the grid. But instead of calling them latitude and departure or X and Y, we call it station, we call it offset. But there is a little bit of a wrinkle to this. It works as long as your alignment is straight, but it doesn't work across the board 100%. So we're going to take a look at some things here. Let's see. Yeah, I'm going to draw a picture here just to make sure everybody's understanding what's going on. So this is called your station, okay? So that's your alignment. That would be like your center line of your road. And your offset is either left or right of your center line. And then typically then you're going to have an elevation above it. So let's go to this diagram real quick. Now we're going to spend a little bit of time on this today, but we're going to move more into this when we get into highways. So that's going to be a lot more important. So let me just do a thing here. So first off, can anybody tell me what a station is? I think you guys do. Most of you should know. Does anybody know what a station is?
A turning point in the traverse.
Okay, it could be. I'm talking about a station along an alignment. Let me qualify that. I do agree with what you said, okay? So let's talk about a station along an alignment. So what is an alignment? Anybody know? Well, it's kind of like a number line, okay? And that number line has a 0 starting point. And all we do is we measure distance along this number line. And so if we measure out 100 feet, we call this 1 plus 0, 0. If we go another 100 feet, this is 2 plus 0, 0. Get the idea? 3 plus 0, 0. Okay, so this one, this would be called my alignment, and this is my stationing along it. Everybody okay with that? Notice which way this is traveling. This is traveling in that direction. So if you put yourself at 0 and you look towards the way it's happening, this is the left side and this is the right side of that alignment, which is important because if I come to this point right here and I measure this distance, let's say that is 1 plus 70, then I have to know whether I'm left of the alignment or right of the alignment. In this case, I'm left. So I would say that I am whatever this distance is. Let's say that distance is 50 feet. Then I would say I am minus 50. So this would tell me to go 170 feet this way, and then you're going to turn 90 degrees and go that way 50 feet. And if you're on this side, and you're at 2 plus 0, 0, that would be 200, or 2 plus 0, 0. And then this would be, let's say 100, then this would be a plus. Okay, that's how your alignments work. So this is basically just a grid. This is your X direction and this is your Y direction. Everybody see that? So what happens when you get on a curve? Okay, so when you get on a curve, if this is where a curve starts, now things change constantly because what's happening, now you're measuring along a bent distance. So at this point, this would be 4 plus 0, 0 measured or bent, and then this would be 5 plus 0, 0. Now here's how the stationing works. The stationing runs radially. So the stationing goes this way, and this stationing goes this way. Can you guys see how complex this gets? Then what I'm going to do is get another straight line, and I'm going to be off the straight line. So this is the way highways work, okay? And this is your offset directions, left and right. So we'll have a lot more to talk about this when we talk about some things as we get into this, okay? So let's go back and we'll cover a few issues here on that. And then I'm going to move on. Let's see. So this is your hybrid. There's your station. There's your offset. And there's your Z value. Again, so highways, pipelines, utilities, they primarily use hybrid systems. So the stationing is a horizontal distance measured along an alignment. So if you're at 0 plus 2563, you're 25.63 feet from that beginning point. And if you're at 12 plus 7201, then you're 1,272.01 feet from that beginning point. So we also use terms full station, half station, and quarter because these are very often used when you do layout. So for instance, when you do a center line alignment on a highway first time through when they're doing rough grading, you're usually staking it out at what's called full stations. So every 100 feet. Excuse me. So when you do other things, you're going to be at a half station or quarter. So when you hear the term full, it's 100. If you're half, that's 50, and at a quarter station, you're 25. Highways don't normally go much below quarter stations unless it's something unique that has to happen, like a catch basin or something. Then they'll have a different station on them. So when you talk about delta stations, that's just the difference between stations. So what we want to do is find the distance from station 5 plus 00 to 13 plus 3180. You just subtract the two, drop that plus, it's just a separator, and it tells you that you're 831.80 feet between those stations. So it's a very, very convenient, easy way to use it. But here's the thing to understand. If this is on a curve right here, that's 831.80 feet that's bent. It's not a straight line. So that varies based on whether you're on a straight line or a curve, or you could be kind of on both. So again, I'm going to have a whole lot more to say about this once we get into dealing with the concept of highways and alignments and that kind of stuff, okay? All right, so Offsets also, the one thing to understand with offsets, the distance left is typically considered negative. Now that's not true by everybody's standard, but that's what we usually use, and right is usually positive. And that is measured either perpendicular to your tangent or radial to a curve. And that concept of radial, that's really, you got to think about that, what that really means. And again, we'll talk about that more as we get into it. So, okay, let's move on. So elevation, that's just your distance vertically above or below your datum. So that's actually the easiest component to handle typically. That's not a big deal. All right, so there are ways of converting hybrid coordinates into station offset or off station offset into northing and easting. So that gets pretty involved, and I'm not going to do that on this lecture right now, but we'll just suffice it to say we'll talk about this a little bit later. Okay, so what we really want to focus in on now over the next bit of time that's remaining, I want to talk about some coordinate geometry concepts just to get you start thinking about this, okay? And we're not going to do all of it today, and then some of it, like I said, I'll be doing this on the board on Thursday, and then next week I'll probably be doing more of this via my tablet here so that we can see it. So coordinate calculations, like we said, you know, they're beautiful the way they work. They speed up all of your work. They give you typically less mistakes. There's just a whole reason of things, a whole bunch of reasons why you want to use them. But what we do, we have several different, what we call COGO types applications or coordinate geometry calculations. And one of the things is what we call an inverse routine. So what we're saying with an inverse routine is we have the ability to determine a distance and or a direction by using two pairs of coordinates. So this is really cool. You have a coordinate at point 50 and another one at point 51, and you want to know what the distance and direction between them is. So that's referred to as an inverse routine. So if you, and you're going to hear me say this a lot, I'm going to say, well, let's inverse between these 2 points. What we're talking about is getting a distance and a direction. So a direct routine says that you can go the other way. So if you have a starting coordinate and you have an angle and a distance, or I guess I should say a direction and a distance from that starting point, you have the ability to calculate a coordinate of that. That's what we call a direct routine. We can determine angles between any 3 points. So you can have a back sight and a vertex and a foresight. So basically you're going to inverse and then you're going to calculate angles. And then you can get some higher level stuff, which are called intersections, where you can take 2 bearings from 2 known points and shoot them at each other. Or you can do a bearing in what's called a distance and intersect them, and you can do a distance. So you do a lot of this on AutoCAD. An example of a bearing intersection is when you take 2 lines that are not touching and you fillet them with a 0 radius. That's a bearing intersection. So what it's doing is it's providing a solution where those 2 lines intersect even though they currently don't on the screen. And when you're doing a bearing distance, you're intersecting a straight line in a circle or an arc. And if you're doing a distance, you're intersecting two circles. And then the last thing we can talk about with coordinate geometry is an area type calculation using coordinates, which is actually pretty slick. So we're going to talk about inverse routines first, then go into direct and angles. And again, I'm going to probably just present it today. I'll get into some of this on Thursday because we're going to need to know how to do inversing and direct routine and angle calculation. So we're going to be talking about this in conjunction with side shots. And I'll be giving you some homework, and then next week we're just going to kind of work on this again. So let me do the presentation here. So inverse can be broken down either through what we call analytic geometry or surveying. So the difference is really just what you're using is whether X's and Y's or northings and eastings. So you just kind of have to be aware of that. So inversing says that you can calculate any angle by taking the delta y and the delta x of a distance and dividing that, and you can get an arctangent relationship. And your distance, I'm going to show you this on a picture here in a minute. Oh, let's see. Well, this is direction. So let me go over here. We'll take a look at what this is saying specifically, and then we'll generate some numbers with this. Okay, so let's take this guy here. So here's what we're saying is I have a line. Now just envision that your grid, I guess I'll draw the grid so we can see it. So we have the grid here, and we have a grid here. And so we know that this is X, and this is Y. So what this says is if you have a point here with an X1 and a Y1, and you have another point here with an X2 and a Y2. So in other words, those are known coordinates and those are known coordinates. You can get the angle of this point here by using this inverse concept. So inverse says this, that you're going to take the arctangent of delta y, which would be y2 minus y1, divided by delta x. Now, one thing that this is important to understand, if I am going from point 1 to 2, it's going to give me this direction like that. Then notice what I'm doing is I'm taking 2 minus 1. If I flip these guys, I'm actually calculating the angle in that direction. Okay, so that's very important when you get into inversing. So if you're going from point 1 to point 2, so this is point 1 to point 2, that's the direction 1 to 2. Notice we're calculating 2 minus 1. So this will calculate this. This is just a y over x relationship. Okay. So if we had this, let's put some numbers here. So let's say that this coordinate value here okay, so we'll say that this coordinate value here is 2, 2, and this coordinate value here is 7, 12. This literally tells me to take that. So delta y would be 12 minus 2. And then I'm going to go 7 minus 2. So if I take 12 minus 2 divided by 7 minus 2, take the arctangent of that, what that'll give me is 63 degree, oops. If you do the math, you get 63 degrees, 26 minutes, and 0 seconds. Now that would be the analytic geometry way of doing it. All right, so let's look at the surveying way, because that's going to be, excuse me, more important. So from a surveying standpoint, basically we now talk about latitude and departure. So it's essentially just going to be your departure over your latitude. And remember, latitude is always going to be delta northings, and departures is going to be delta eastings. So what we're always going to do, calculate our latitude first and then our departure from our coordinates. And again, notice if we are traveling from 1 to 2, then it's 2 minus 1. Okay, so let's look at this picture again, just to show you the difference. And I will be, like I said, we're going to be working a lot of problems out on the board, so just kind of try to absorb this right now, and you'll catch it as we get into it. So I'm going to change this up here. Dang it. I'm going to, let's see, select. Let me just kill this real quick. Okay, so this time, let's assume that what we're going to do, if you recalculate this, we'll use 1 and 2 again, but we're going to actually do it as a surveying application. So what you're going to do in surveying, you're going to use latitude and departure. Okay. So let's flip something here. So if this is actually surveying related, this would be 12,7 in terms of northing easting. And this is still in northing and eastings. Okay. The difference here is what we're going to get is the angle off of north. So what this tells you to do is calculate your lat first. Latitude would be your delta northings, so that would be 12 minus 2. So your northings are 12 minus 2. That's your going to give you 10. And then your departure would be easting of that minus the easting of that. And again, notice I'm traveling, that's just saying I'm going from 1 to 2. Okay. So when I calculate this angle, it's your departure over your latitude. So when you do that, let's see, I don't know if I have calculated that. So you should get 26 degrees, 33 minutes, and 54 seconds. Now, because this angle is a bearing angle, we have to put it in the quadrant. So the way we determine that is up here where it has 12 minus 2, you get a positive. That means this is actually north, and this is also east. So this bearing would be northeast. So the only thing that we have to do differently than when we do analytic geometry types of things is when we calculate our latitudes and our departures, we're going to do it based on the positive signs, and we're going to calculate positive, negative, and we're going to get the bearing. So we'll be working a lot more problems of this nature as we get into it. So just wanted to show you that that's the process, but you've just got to remember that if you are north, you're positive, south is negative for latitude, and for departure, east is positive, and west is negative. So this is what we call this process right here, doing this and this. This is an inverse, and this is an inversing an angle. Okay, so we're inversing right here, subtracting coordinates is inversing, and then what you're doing is calculating a direction at that point. So let's go over and look at distance. Distance is easier done. Okay, so this screen right here is probably the most important one. We're not going to look at analytic geometry. You can, and they do that, you know, in math classes and stuff, but we don't need to follow that as much. And like I said, if you're not following this yet, you will get this. This is pretty simple. But this is the definition of inverse right here, basically just subtracting your northings from your northings and your eastings from your eastings. But what's really important is this is implying you're traveling from 1 to 2. If I'm going 2 to 1, I would reverse these. So that's the thing that determines the sign, okay, when you do this. So that's all critical. So this little chart, again, we just looked at that determines your bearing quadrant. So when you get your delta northings or your delta eastings, you go look at whether they're positive, negative, whatever. If you flop the quadrant, the coordinates, you're going to get the wrong sign. So that'll put you in the wrong direction. So we'll have a lot more to say on that on Thursday. Okay, so inversing distance is real simple. It's just using the Pythagorean theorem. So what we would have for distance would be delta x squared plus delta y squared square root analytic geometry. But in surveying, it's always going to be latitude squared plus departure squared square root. You will typically never make a distance mistake with surveying, but what you will make is probably a direction change mistake. That's your biggest issue right there. Okay. So if you go the other direction when you're talking about surveying, we're looking at what's called a direct routine. So what this is saying is that you have gone out and you know a distance between a point and another unknown point, and you know its direction. So you can calculate a coordinate for that based on knowing those two conditions. So what we're saying, let me see if I get a picture here. I don't think I do. Oh, let's go and look at a picture here. So what we're saying is, if you have a known point, and let me draw my, this will be a lot easier to see on the board, believe me. So when we get into class, okay, so this is my easting direction. This is my northing. What we're saying with a direct routine is we have, let's say, a point A here, and we have a point B, but we don't know the coordinates. So we do have a good northing and easting for A. We know that. And we know this, which would be either in terms of angle or, azimuth, or let's say bearing. And I also know this distance. By knowing this and this and this, it allows me to calculate that. So what that basically said was you can take your northing of B is going to be equal to your northing at A plus the latitude A to B. And that should look familiar because we used it last week. And then the easting of B will be the easting of A plus the departure A to B. And we're going to use this when we get into the side shot concepts. So we're going to see that quite a bit. So I have just going to see if I could get you a diagram here or something we can look at. All right, so I'm going to draw a picture here, and we're going to determine some things, just see if we can utilize this concept a little bit. So I'm going to say, let me clean this up. If you have a calculator, you might want to pull it out and work this with me. But again, like I said, we're going to work some of this on the board. So I'm going to assume north is up on this diagram. And I've got a picture. Let me just draw really kind of a rough picture here. Keep in mind that everything's going to be in terms of northings and eastings at this point. So this point is point 50. And his coordinates are 5,000 north and 5,000 east. And we have another point here. This is going to be point 51. And his coordinates are 50, 64. I'm going to keep it simple. But normally you would be working with decimal places. So we're going to do it really simple today. 47, 58, and that's also 0, 0, 0. So what we want to determine, again, let's assume, let me make another notation here, that in this diagram, north is up. You should be able to CET. That's north. Because, you know, in terms of northings and eastings, this guy has a higher northing than that guy, and this guy is a lesser easting than that guy, so that would put north straight up. So what we want to do is we want to inverse this line, and we want to know what is the distance and what is the direction on this guy. Okay. Now you may only be interested in the direction, you may only be interested in the distance, so you don't always need to calculate both things, but for some applications you do. So here's what we're going to do. It's kind of a several step process. First thing I'm going to do is calculate latitude and departure. So I have to know this too, which I didn't define. I want to know what the direction is from 50 to 51. So the latitude is going to be from 50 to 51. So when we write this, that's going to be the northing of 51 minus the northing of 50. If you reverse those, you're going to get the wrong sign, okay? So 51 is that, and 50 is this. So that gives us a latitude, 64. And that's positive. So departure from 50 to 51 works the same way. That's going to be the easting of 51 minus the easting of 50. So notice I'm going 50 to 51, so that I reverse that. So the easting is 4758 minus 5,000. So notice we get, we get a negative 242. Can anybody tell me why it should be negative?
Because you're heading west.
Correct. So you can see that if you flip these, you're going to get the same number. You're going to get the absolute value, but you're going to get the wrong direction, and that's going to kill you, okay, in this problem. So it's very important that you get these signs right, okay? Because flipping them, I get the absolute value, but it just screws me up. Okay, you guys understand that? So for the direction in terms of bearing, and remember what you're going to get is a bearing out of this. So the angle is always going to be between 0 and 90. It's departure, 242 divided by the latitude. Now, I don't worry about the negative signs because they are only telling me quadrant, so I don't care about them. So I'm going to take 242 departure divided by 64, and then I take the arc tangent of that, and I got, you guys can verify this, looks like I got 75 degrees, 11 minutes, in basically 12 seconds when I round it to the nearest second. And so because this is traveling north, and that's negative, that would be west. So that would be the direction on that line, okay? And if you think about it, it should make sense because you're not as much distance in the latitude as you are in the departure. So this angle has to be pretty great, okay? So if we look at the distance now in this case, the distance is real simple. And you'll always get the distance right, even if you have the sign wrong here, because when you square a negative number, it becomes positive. So it doesn't matter. But with angles, it really matters. So you have to, your angles are going to be the thing that is going to be the real kick, the real key there when you do that. So let's see what we come up with. 242 squared square root. So if you guys are following me from a math standpoint, I get like 250.32 feet. And by the way, I'm assuming, if I say this is feet, I'm assuming that these coordinates are in feet. So if they're metric coordinates, then you're going to be in meters, those kind of things. Okay. So this is a process. This is what we call an inverse process. And it's really, really important to doing anything that you deal with. So let's do a real quick direct routine. Okay. Really, like I said, we've really already done that because we did that when we did coordinates the other day. But let's just do a different example here. So let's say you have this line right here. Now let me do this a minute. All right, let's say let's say you know this coordinate, and it's at we're going to call this, let's say, just 0.5, and he's sitting here at 5,000 north and 5,000 east. So we know he's north and he's east. And let's say that you measured, let's say you backsighted this point, and you know that this backside has a direction of north. Let's say it's, I'm going to say it's like maybe 40 degrees, 12 minutes, and 32 seconds east. So you set your instrument up, you hit your backside, and you turn this angle here. And we'll say that angle is 89 degrees, 25 minutes, and 39 seconds. Okay, angle to the right. And this picture, that we also need to know that north is up like this. So we're going to say this is north, like this. Okay. So you also shot a distance here, let's say of 560.26 feet. So we got this point out here. We're just calling it 100. We need to know what is the northing and the easting of this point. We don't know that. So this is not an inverse. This is what we call a direct routine. So who can tell me what we need to do first? Nobody has an idea?
Find the direction.
Yes. Okay. So how are you going to do that? This is what we backsighted, and we know the direction on this line. It's traveling that way, 40, 12, 32 northeast. You agree?
Oh, you calculate the bearing of the line that's 560.
Okay. How do you do it?
You add the two
Okay.
angles that we have, and then you
Yep.
subtract 180 from that.
Well, let me ask you something. What you did was fine, perfect. But do you need to put it into a bearing?
No, you can use the azimuth.
Right. So actually, when you added the
both of
two
those is
together, guess what you had?
That's the azimuth.
That's your azimuth. The beauty of using the azimuth is that we don't have to worry about the quadrants. Okay. So your first solution was perfect, but I can convert that to an azimuth really easily by taking that azimuth from 5 to 100 is going to be equal to that bearing, because it's a northeast quadrant, really simply. I just take that guy plus the measured angle, and I have an azimuth. And then I can use that very easily. Let's see what you guys verify this. I got 129. I just made this up, so if you guys see something different, let me know. I got 129, 38, 11, and that would be my azimuth north. Anybody agree with that? Was that yes?
Yeah, that's right.
Okay, cool. All right, so now all I need to do is calculate a latitude and a departure. All right, so what I can do, my latitude from 5 to 100 is the distance, 560.26 times the cosine. Remember, we're always using that cosine in this case. That's another advantage to using the surveying relationships. We don't ever have to worry about that. That gets me, I have to, hold on a minute, I have to calculate it. You guys can verify it for me. And we will be doing a lot of this on the board. So, you know, once you do this a bunch of times, you get real quick at it. Oh, crap. Well, I say that and then I just lost my number. Let's see, 129, 38. I got a negative 357.397. Anybody get that number?
I got the same.
Yeah, this.
Does the negative make sense?
Yeah, because we're going down.
Yeah, absolutely. Now my picture may not be totally 100%, but yeah, it does make sense. All right, so let's see what the departure. Now we're traveling east, so shouldn't the departure be positive?
Yes.
Yeah, so let's see what happens here. So we're going to do a cosine, or a sine rather, times that 129, 38, 11. So my departure, 5 to 100. Let's see. Sine.
$431,460.
You're ahead of me. Hold on. 431, 461.
I got 461.
All right. 431, 461. I agree. And positive is exactly what we said, right?
Yes.
Makes total sense, right? Because it's going east. So we got our lat and the depth. So all we do now is we say, so the northing of 100 is going to be the northing of the point we're coming from, which happens to be 5,000, plus that negative 357.397. And that's just really subtracting that. So we have 5,000 minus 357,397. If I did my math right, you guys verify 4642.603. And my easting is the easting coordinate of 5 plus the departure, and that is a positive departure. So we get 5,431.461. So what we just did there, this process, this is called a direct routine, okay? So you're taking an angle or direction, converting it, and then you're getting a latitude and a departure and getting it into coordinates. So those are the two big things that we're going to be concentrating on. Then I'm going to show you some other things on Thursday that we can do with inversing. This is really, really, really powerful stuff. It's real simple. It's really easy. And if you follow, like azimuth works great. Hopefully you see that. Okay. Any questions anybody has? right, so this is that's what we just did there. The direct routine, calculated the latitude, and then calculated the coordinate. So we're going to kind of revisit some of this stuff. I'm going to give you guys some homework. We'll talk about area next time. I'll do some other things with you, coordinate geometry based. But we'll get in. I'm going to talk a little bit more about this state plane concept next week. So this is a good place to stop. So if anybody has any questions, I'm going to go ahead and pause the recording.